All right, let's get into it. Today, we're pulling back the curtain on something we use every single second but probably never think about: the internet's invisible nervous system. We're going to explore the absolutely brilliant, super complex logic that makes everything from your video calls to those huge downloads even possible. So, let's dive right in. So, have you ever stopped to think about this? You're on a super important video call, right? The picture is crystal clear. But at the same time, in the background, your computer is downloading a massive game update. How in the world does the internet know which data is more important? And how does it manage to do both at the same time without just grinding to a halt? Well, I'll tell you, it's not magic. It's actually a set of incredibly smart rules. Okay, so the secret to all of this? It lies in what we call the network layer. The best way to think about it is like the internet's global postal service. Seriously, its one and only job is to get these little chunks of data, called packets, from a source all the way to a destination. And it doesn't care if that means hopping through dozens of different computers or routers all over the world. This is the bedrock, the foundational layer that's responsible for that entire end-to-end journey. So if the network layer is our postal service, you can imagine its first challenge is, well, it's immense. I mean, with millions and millions of routers out there, a single data packet has literally trillions of possible paths it could take to get where it's going. Choosing the single best one, the fastest, the least crowded, is this monumental puzzle, and it has to be solved in microseconds. The solution? It's all in these amazing things called routing algorithms. Now, this right here, this is the fundamental logic behind all smart routing. It's called the Optimality Principle. It might sound a little academic, but the idea is actually super powerful and kind of simple. It basically says this: if the best route from, say, New York to LA happens to go through Chicago, then the path from Chicago to LA has to be the best route from Chicago to LA. See? It's like a chain of best decisions. This little principle is what lets us build these perfect, super efficient long-distance paths. It's how we break a massive global problem down into smaller, totally solvable pieces. So, one of the first ways we tried to solve this was with something called distance vector routing. And I love this analogy. Think of it as routing by rumor. It's perfect. A router doesn't have a big map of the whole internet. Nope. Instead, it just asks its immediate neighbors, hey, what's the quickest way you know to get to, say, Google servers? It then gathers up all these little rumors from its friends and compiles them into its own list of directions. The key thing here is it just trusts what its neighbors tell it, no questions asked. But what happens when a rumor is wrong? This is where the whole thing falls apart. It's the algorithm's critical flaw. So imagine a router, let's call it router A, suddenly goes offline. Its neighbor, B, will eventually figure this out. But then B might hear from its other neighbor, C, who says, hey, no worries, I can still get to A. The problem is, C's path to A was through B. You see the loop? So B thinks C has a path, C thinks B has a path, and they just keep passing this bad information back and forth forever, convinced a path exists when it absolutely does not. This crazy situation is called the count to infinity problem. Okay, so to fix this whole bad rumor problem, modern networks use a much smarter approach. It's called link state routing, and the philosophy here is completely different. Forget relying on hearsay from your neighbors. The goal now is to give every single router a complete, totally up-to-date map of the entire network. Think about that. If you have the full map, you don't need to ask for directions. You can just calculate the absolute best path to everywhere, all by yourself. So how does it build this amazing map? Well, it's a pretty systematic 5-step process. First, a router just looks around and discovers its direct neighbors. Simple enough. Second, it measures the connection quality. You could call it the cost to each of those neighbors. Is it a fast link, a slow one? Third, it bundles all that info into a little packet, a link state packet. Now here's the key part, step 4. It sends this packet out to every other router on the network. This is called flooding. And finally, step 5, once a router gets all these little packets from everyone else, it can piece them together, build that full map, and then boom, it can calculate the best path to literally any destination. So this really lays out the trade-offs perfectly, doesn't it? On one hand, you've got distance vector. Yeah, it's simple, but it's also slow and super unreliable when things go wrong. Then you have link state. Okay, it's more complex to get going, but it is incredibly fast, robust, and accurate. I mean, the key takeaway is pretty obvious. Having a complete, accurate map, even if it's a bit harder to build, is just fundamentally better than trusting secondhand info from your neighbors. For what we need the internet to do today, the choice is a no-brainer. All right, so finding a path to a server that's bolted to the floor in a data center, that's one thing. We've got that figured out. But what about your phone? Think about it. It's constantly moving, hopping between your home Wi-Fi, the coffee shop's Wi-Fi, and different cell towers. How does a data packet that was sent from a server halfway across the world find a destination that just won't stay still? Well, the solution is pretty clever, and it involves two specialized players. First up, you've got a home agent. Just think of this as a router on your permanent home network that acts like a personal mail forwarding service. Its whole job is to keep track of where you are right now. Then, wherever you happen to be visiting, there's a foreign agent. That's just a router on the local network that's in charge of handling all the visiting devices, like your phone. So here's how this all works in practice. A packet gets sent to your phone's permanent home address. Your home agent, acting just like that mail forwarding service, grabs it. It knows you're not home, you're out and about, so it wraps that original packet inside a new one. And this new packet is addressed to the foreign agent where you currently are. This whole wrapping process is called tunneling. The foreign agent gets the package, unwraps it, and finds the original packet inside, which it then delivers right to your device. It is an absolutely ingenious system that makes sure your data can always find you, no matter where you are. Okay, so we've figured out how to find the best path, even to a moving target, like your phone. That's a huge step. But, finding the road is only half the battle, right? What happens when that perfect digital road gets completely clogged with traffic? I'm talking about a massive digital traffic jam. This is the problem of congestion, and believe me, it is just as critical to solve as routing. So what is congestion? At its core, it happens for a really simple reason. Routers are getting data packets thrown at them way faster than they can send them out. It's like a funnel that's too small. This can be caused by all sorts of things. Sudden bursts of traffic, maybe the routers themselves have slow processors, or they just don't have enough memory to line up all the incoming data. And when this happens, when the router gets overwhelmed, it has no choice but to start throwing packets away, just dropping them. Now, it's really important here to understand the difference between two related ideas. First, there's flow control. This is a private, point-to-point conversation. It's like you telling a friend on the phone, "Whoa, slow down, you're talking too fast." It's just between one sender and one receiver. But congestion control, that's a global issue. That's about making sure the entire network, the whole highway system, doesn't get overloaded by everyone's traffic all at once. It's about protecting the whole system, not just one conversation. So how do we actually protect the network from grinding to a halt? Well, one of the most effective ways is a technique called traffic shaping. And the big idea here is to be proactive, to prevent congestion before it even starts, by regulating how data flows. So instead of letting apps just send data in these wild, unpredictable bursts whenever they feel like it, traffic shaping steps in and smooths out that flow, turning it into a much more predictable and manageable stream. And this brings us to our final big problem, and it's probably the one you feel the most every single day. Look, all data is sent in these little packets, but let's be real, not all data is created equal. Should an email you sent be treated the same as your live video stream? Of course not. An email can be delayed by a few seconds, who cares? But if the packets for your video call get delayed, the whole thing just falls apart. This is the whole challenge of what we call quality of service, or QoS for short. This table just makes it crystal clear. Take email. Does it care about a little delay? Nope. Does it care about jitter, which is just the variation in when the packets arrive, some early, some late? Not at all. A few milliseconds here or there means nothing. A big file transfer, it just wants a ton of bandwidth. But a video call? Oh man, it is super sensitive to both delay and jitter, and it needs a lot of bandwidth too. So to make our internet actually work, we absolutely have to treat these different applications differently. So one way to manage this is with a clever algorithm called the leaky bucket. Just picture it, a bucket with a small hole in the bottom. You can pour water into it as fast as you want, in big bursts even. But the water only drips out of that little hole at a steady, constant rate. Now what happens if you pour too much water in too fast? The bucket overflows, and that extra water is just gone. It's lost. In network terms, this means the leaky bucket enforces a really rigid, smooth output of data. But if a burst of traffic is too big for its buffer, it just has to discard those extra packets. But there's a more flexible approach, and it's called the token bucket algorithm. So here, imagine the bucket collects tokens at a steady rate. Think of tokens as permission slips to send data. To send a packet, you have to cash in a token. And here's the brilliant part. If your connection is idle for a while, you don't use tokens, so you can save them up. This lets you then send a big burst of data later on by spending all your saved tokens at once. It gives you that bursty flexibility while still controlling the average rate over the long run. So here's the crucial trade-off. The leaky bucket, It creates a perfectly smooth, predictable stream of data, but it's super rigid and will actually lose packets during a big burst. The token bucket, on the other hand, is much more flexible. It allows for those bursts that a lot of applications really need. And get this, it never discards data packets. It only discards tokens, which is just the opportunity to send data if you don't have permission. It's a much smarter trade-off for most modern uses. So let's just step back and recap this incredible toolkit that makes the internet work. We've got these super smart routing algorithms like link state that are constantly building live maps to find the absolute best path. We have this clever system of home and foreign agents to track us down and deliver data even when we're on the move. We have proactive congestion control using traffic shaping to prevent digital traffic jams before they even start. And finally, we have quality of service, which understands that not all data is the same and makes sure your video call doesn't buffer while an email downloads. It's amazing. And that brings us to the future. I mean, think about it. All these rules we've talked about, they were designed for a world of computers and phones. But what happens when billions of new devices come online? I'm talking about smart cars, smart homes, entire smart cities with sensors everywhere, all communicating constantly. How will this hidden intelligence have to evolve to manage a level of complexity that we can barely even imagine today? That right there is the next great challenge for the internet.